Okay, so let's go back. How can I, like if I don't know what the shape of the problem is, how can I skip this encoding thing altogether? I have to kind of use a more powerful nonlinear function, or seeing it as in a slightly different way, I have to move the encoding step inside the network. So now I use something like a generalized perceptron for people that knows what it is. So what it is I just stack a bunch of linear models. So now, simply stacking linear models alone is not very useful, because a linear model stuck on top of another linear model is a new linear model, and I can just multiply the coefficients internally, and it collapses to a single linear model. So to get power out of this, I need to intertwine linear models with some nonlinearity that prevents this stacking from happening. Now, what I'm doing here, you see, I'm using this shorthand notation because typing linear layer is cumbersome, and you can inherit what the input is from the output before. So very quickly I can write 10 tan h 10 tan h1, and what this is doing is basically creating, is taking a number in, or in our case it's taking these two numbers because we're in 2D, is creating a linear combination of 10 numbers, and then is applying hyperbolic tangent, which is a kind of historical choice for nonlinearity. And so basically this is a linear combination of 10 different hyperbolic tangents with different coefficients. And then I do it again, and then I sum everything together. So this part here is kind of creating a representation, a nonlinear representation of my input. The difference from before is that this is this is very neutral. This is completely open, and I can learn it from the data. Is more effort for the optimization because I have to learn the encoding, but is more general because if I don't know, and in general I don't know, like for example, I don't know what is a good way to model the distribution of images in the real world. I want my network to learn what cars look like just by looking at cars. I don't want to make assumptions on the first picture should be red and the second picture should be blue. I want something very generic. So I create something like this. The structure of this is something like this. So if you look at each point here is like a neuron is the number. So I start from two inputs. I create a linear combination, and here I'm putting like different colors to symbolize that the weights, what was alpha before, they are different. You can imagine that the blackness is the absolute value. So when this is very dark, there's a strong link, either positive or negative. Strong correlation. When this is very light, there's light correlation. And then I have element wise. You see, very simple, element by element. And then you start seeing why these linear combinations are expensive, because now I have 10 elements combined with 10 elements, and this is 100 weights. And this shows clearly why these linear combinations are one of the most expensive parts of neural networks, because they scale with the square. Then I do another nonlinearity, and I recombine everything here. So now something like this is basically just like this. I have like my input times all my coefficients plus my my offsets or biases, and then my output. Yeah, this is basically input and output. Now let me see if I had to define something that I didn't define. Network. Don't think I really need this. This will be close, nice and easy. Now I can do this, and you see now validation is going down like a lot more slowly than before, because now I have a lot of parameters. I had like 4 parameters for the linear combination of 5. Now I have what is this, like times 5, 50 here, then a few here, then a few here, like 60 parameters. And you see now that I actually have 2 different rates. The training is going down the loss on the training data is going down much more quickly than on the validation data. And so now it's kind of important to kind of do a training. This I kind of let it go for more and look at the loss. And I can actually, again, oh yeah, this is okay. Sorry, forgot one thing. This is important. Here I'm using slightly different syntax. It's in network, training, option for validation, and I'm putting all here. This is something that you almost always want to do because this is kind of a property that you get out of the training. The default property is the train network, which is nice for examples. But for serious application, you want something like this, which is an object. And from this object, you can retrieve the network, but also informations, like losses and things like that. Yeah. So it's always, my advice is always better to get the object out and then query it for things, because you don't lose anything this way. Yeah, you get the complete information about the training. So you see, here I'm querying the object for the loss, and here I'm querying the object for the train net. And now you see this is a lot more very different compared from before. Yeah, because as I said, you can see these in two ways. Like either I'm putting a random nonlinear function and leave it at that, or you can say, this is a linear combination of hyperbolic tangents. And a linear combination of hyperbolic tangents will have a very clear generalization rule. They are stuck between 0 and 1 plus times a coefficient in front, so they will be pretty stable outside. And you see, I have a lot of parameters. So you see what happens. Like the function here follows very closely my red points where I have red points, but this has zero generalization. Yeah. So before I had some general outward knowledge about my problem, and this is why I say it's always better to put it in. In this case, I had kind of to learn the representation, and it completely fell over at the boundary in this case. And the boundary is often defined by how you pick your nonlinearity. There are several ways. There's sigmoid, hyperbolic tangent, which is just scaled version. There's soft plus. ReLU is a very popular choice. Is kind of linear activation unit. It's called. This is doing the ramp function. Is the identity on the positive and 0 on the negative. This is a very popular choice because it's very fast to compute and it's very quick to train. It has some limitation. Like I'm taking a derivative, and you see if you multiply something by 0, the derivative, this part here is completely flat. So you have you need to regularize input a bit to use this, and you have like more kind of modern sophisticated activations like this Swish Mish. There are several that are they don't go. They basically they extrapolate here to a linear function and to 0, but around 0 they have some nice nonlinear behavior to actually go somewhere and not stuck the training. But of course they are a bit more expensive to compute. So for example, what happens, and here just fancy introduction to use net replace. What happens if I replace my hyperbolic tangent layer with something like Swish? Yeah, let's do this. Let's do the training. I have different, I can do this for a bit. And then I evaluate. I don't know what this was, so I'm just gonna reevaluate this. This was nonlinear fit 2. And I get, this, this approximate to a linear function at infinity. So I get a very different out of distribution behavior. Yeah. So in general, you are in a very high dimensional space with these neural networks. But I think it's interesting to see this at also at kind of lower dimension where you can appreciate what exactly happens when for a particular choice of activation functions. Okay, so let's go back to the XOR. Let's go back to the XOR and use kind of a classical choice here. So what we do here, we can imagine that my first part here is the feature extractor, the very neutral feature extractor. And the second part here is the linear approximation. Sorry, is a linear combination of my features. Yeah, so here I have 5 features that I recombine them and do my classification. Okay, so this is not linear. Is this able to handle it? Okay, so now it's doing something. You see, this is getting some color. It's getting the right color. So this again, I solved the problem, by adding more power to the network. This is a very dangerous trade-off, yeah, because you can always add a lot of parameters, and so the risk is always, both to overfit or to make it, very unwieldy to train. It's going to be very difficult to train because you have a lot of parameters. So this is a bit of trial and error. This can be very powerful if you add, the right amount of parameters. You are just powerful enough to solve your problem. So in this case, you see this is going down nicely. This is, this model is not too difficult to train, so it's going down nicely. And given that I have, again, in the spirit of having like automatic goodies, given that I have a softmax here and it's using cross entropy, is also doing some automatic measurement for you, and is adding this error rate, because it's a nice parameter to do. The loss is, kind of, you can have like some scale. It can be, -1, like 10 to the power of -2 or 1. But for classification, you typically want to see the error rate. So now, is 0. It has learned everything. So now, if you plot this, you see this is now how it's segmented the space between the two classes. So it has actually now learned the problem.